Hello everyone, I am back with another video. In this video I have received a request from one of the subscribers that the subscriber was struggling to simulate the upheaval buckling of a surface laid subsea pipeline, and especially due to an imperfection which is caused by a seabed movement. So that's what we're going to do in this session. What you will learn in this session would be how to model a long pipeline for global stability analysis, then how to create pipeline-seabed interaction, and how to perform UHB analysis, which is upheaval buckling analysis, using ABAQUS Explicit. I already have videos on using Rick's method and static analysis in ABAQUS, so you can have the look at those to do a similar analysis with that. But however, those analysis may come back to you with a lot of divergence and convergence issues. So it's in this case I'm showing an ABAQUS explicit way of doing it, and our model is not big, so it works fine. So it can be afforded in this case. And finally, post-processing the results. So now the problem description is like this: that you have a subsea pipeline which is laid on a seabed. So this is your seabed. And obviously in the first step, what we're going to do, we're going to apply a gravity load. We will fix this end of the pipe. We will fix the seabed to move in any direction. This end will be free. And then we will just apply gravity load so that this falls down on this and creates a contact, so in a stress-free state. Okay, and the pipeline length in this case is chosen to be 3 kilometers. The diameter of the pipeline is 323.9, apologies for this error, millimeters, and the wall thickness is this. Again, you can play around with those in the model if you have different problem. And also the length comes from the fact that you are going for a length which can give you kind of a overall representation of the global response, and it is far away from the area of concentration. In this case, the area of concentration will be this area, and I will come back to that in next few minutes. Next step would be to move the seabed or simulate the movement of the seabed. So this will already be in contact with this seabed in a horizontal way, and then once the seabed moves down due to anything which is happening in the sea itself, and your seabed is start to move around, then that seabed movement will be around 1 meters. In this case, everything remains the same. Pipeline edge on this edge is fixed while this edge is free, and this seabed is again fixed while this seabed moves down without any horizontal motion or any orthogonal motion to the screen. So that's what we're gonna do. So pipeline obviously will go and follow this kind of path once it's there, and this will kind of create an imperfection in this area of the pipeline, somewhere in this area, and that's the area of interest. And then we will apply the operating conditions, which will be temperatures in this case, and based on that we will see if the temperature goes up to 120 degrees. Generally 60 degrees is fine, but I have just used this random value to show the whole buckling curve for the force, effective axial force before and after the buckling. So this is what's going to happen. We will apply a constant temperature all around the pipe, and we will see, and we will fix this edge of the pipe now to move in the horizontal direction, so that we can create a constraint, and then based on the temperatures and thermal expansions, the pipe will start to buckle due to the imperfection in this area, and that's what we want to capture in this case. Okay, so the material properties and assumptions, some of them I already told you. We will assume the pipeline to be elastic in this case, so we are doing an elastic buckling analysis. These are the properties which are used. Steel density used in this case. Coefficient of thermal expansion is given as this value, and we assume the seabed to be rigid. Again, if you have the properties for the soil available during and after the movement, then you can use those. And again, defining the material properties for soil will be very similar to what you will do for any other material. So you can look into that if you have anything like that. But for this case, it was enough to go with a rigid seabed, so that's what we're going to do in this case. And then we will define an interaction between the pipeline and the seabed, and in that case normal contact will be defined with the hard contact. This means the contact pressures will be computed based on the individual stiffnesses, and also the friction coefficient is assumed to be 0.5. In reality, for the first two steps, you can also set the friction coefficient to be 0 because there is not much lateral motion. but for the last case, when you have a lot of upheaval buckling, then the friction may play a role. So you can again apply any value you have. In this case, I was provided with this value. Okay, and what we're going to achieve at the end of the day, so this is our pipeline. These are the two segments of the seabed, and you see the temperature is not rising initially. The step one is the case when you only apply the gravity load, so it's trying to establish a contact. You can see this analysis is going on. After 1 second, you see now it's in the stage where your seabed starts to move down. You see here as well. So this is isometric view, this is the front view, and you can see pipe also starts to go down with the seabed, and you can see there is some kind of imperfection. And then the third step is where your temperature increases, and you see as the temperature increases, your pipe starts to buckle, and at different stages of the deformation you can capture how the force is changing in the axial direction in the pipe. You can also measure the displacement here, and you can plot the same here as well, and you can find out what is the maximum deflection of your pipeline after this load. So you can see it goes up to a buckling point, and then you have a post buckling results as well, and obviously it's an explicit analysis, so it doesn't really give you any problems with the convergence. So just to show you again, first step, everything only gravity load. Second step, which is after 1 second, if you see here, we will move the seabed down to a distance of 1 meters as prescribed before, and the pipeline will automatically follow the path and will create a kind of imperfection. And the last step would be the operating condition of pipeline, where temperature will be increased from 0 to 120 degrees, and as the temperature increases, you see this imperfection causes buckling in the pipeline, and that's what we have captured here. So now let's jump into ABAQUS and see how we can do all this. I will quickly go through it in ABAQUS. Okay, so this is the model, and I already showed you this animation before, so just to show you that this is the model. We are in the visualization mode, which is the post-processing of this job. So you see the first step is basically doing nothing, it's just that gravity, so the contacts are established. And in the second step, I have removed the contours, but you can bring them back anytime. So you go to viewport options and maybe legend, title block, whatever you want to bring in, so you can bring all these things as well. So you see the temperatures are all like random right now, which is 0 in this case. So that's how it looks like. Now in this case the seabed is moving down, and if you go forward, then you will see the pipeline now starts to heat it up, and the temperature is increasing. That's why the pipe's color is changing in this temperature spectrum, and you see the buckling is going on right now, and pipe is going up, and that's what we have captured there. So now let's see how we can do it. So let's go to the part and see what I have done to create this job. So what I have done here is I have created 2 parts. The first part is basically the pipe, which is 3000 meters long, and what I have done here is I have created the pipe as a 3D deformable wire. So if I can show you that, so it's basically based on the fact that you go to part 3D deformable and you select wire, and then you select planar, and then you create a line segment. So if I press continue here, just create a line from 0 to 3000, and that will give you your pipeline geometry. Then the next step would be to create this floor. So what I have done in that case is I have created a shell here. So what you do is you go to again 3D, and now you go with a discrete rigid, and then you go with a shell and you make it planar, and then you make this rectangle. Again, I have chosen this to be half of the seabed, because half of the seabed has to move down. So this is 1500 times 200. Again, this 200 is just my own imagination. You can use more, you can use less, because pipeline is not moving in the horizontal direction much, but I didn't want to have it go in the lateral direction, so that's why I choose this, because if it goes in lateral direction and it's out of this surface, then it will go downwards, and we don't want to do that in this case. So that's why I choose this length, and pipe will be in the middle of this when we assemble it. So that's what we have done here for the part. For the property, obviously we only want to define the properties for the pipeline. So what I do, I just go to the material, I create a material, and then firstly I define the density, which was 7850. Then I defined the elastic constants, which were 206 gigapascals and 0.33, and I also defined the thermal expansion coefficient, which is this expansion here, and you give the value here. So if I show you the values which I have used now, this is my density, as I told you. My elastic constants are the same, 206 gigapascals, so it's exponent 9. Everything is in meters, so I'm using Newton per meter square, and everything consistent units. Poisson's ratio is 0.3, and the thermal expansion coefficient is this one. So that's my material property. Then what you have to do, you have to create a section. So for that I have created a beam section. So what you have to do is, how to create that beam section is, you just go to create, you select beam, and you select beam here, okay, and then press continue. When you press continue, you will get this window, and in this window you have to define which material it is made up of. So obviously we have already defined material 1, so I will select that. In addition to that, we have to tell what is the cross section of this pipeline. So for that I have used profile 1, and profile 1 is basically, you just press create profile, you select pipe, and here you prescribe the radius, because it was, if you remember, the diameter was 323.9 and thickness was 12.7. so I just computed those and I substitute here. Again, based on the D over T ratio, you can select thin or thick wall pipe. In this case, D over T ratio was well above 20, so I just assumed it to be a thin wall pipe, and then I select that here. So if you want to see the values I have given here, for that you go to the profile manager, and you can see so this is the pipe profile which I have used. So this is the half of that diameter, which was 323.9, and this is the thickness in meters. So everything is in meters here as well. So this is how you define the section, and then you just press assign section and you select this and then assign the section. So you see the section is already assigned to this material, to this pipeline. We don't need to define anything else to other things. So we go to the next one, assembly, and we bring all the parts together. You just select these two parts and then you bring them here, and then as you see, your first part is this pipeline, then you bring the other part, and you will see the other part is basically not orthogonal to this pipeline, so you will have to rotate it, and it's pretty easy. You just press this, you can translate, you can press the rotation, select the object, and maybe I will show you that how you can do it. So firstly you need to select the axis of rotation, so you rotate it from this along about x-axis, so I will say 0 0 0, and then you're defining the axis about which this whole thing will rotate. So once you have done that, then you give the angle, and you see this one now will become orthogonal to this one, because I'm giving a 90-degree angle, and it rotates around x-axis. So you see it's rotated around x-axis or about x-axis. So that's what I have done here for all the cases, because in my case actually they were actually in this kind of shape, so I had to rotate both of them. So this is how I've arranged everything. If you look at this xy coordinate, then you see there is this, they look something like this. So pipe is on the top of this, and that's what you have to do here. Then you can go to step, and then you create 3 dynamic steps. So you remember we had 3 steps. In the first step we will only apply gravity load. In the second step we will move this part of the seabed downwards, and the third part we will apply temperature and fix this end of the pipe in horizontal direction and see what happens, and we see some buckling there. Okay, another important thing is basically when you always create a rigid parts like these ones, part 2, you always have to create a reference point. So you can always do this by going to the tools. There are different ways of doing it, but I do it this way, and you press the reference point and then you can select a location. So I have created a reference point on this side for this case. Okay, I hope I am not missing anything here. Next, assembly steps I already defined. So for steps, if you look at the steps, you see that everything is just default. I don't change anything. Its total time is 1 second. Everything is just random and default, whatever is the default value. So I don't really mess around with anything in this. So I just create the step and that's it. 3 steps are there. For outputs, we are also going to apply temperature in the last step. So we need to take the temperature as an output. So for the defaults, I just go to add it, and then I go to thermal and I selected the temperature so that I can see the temperature as well at the end once I process the results. You can also select any other quantities which you require. Then you go to the interactions, and interactions are again very easy in ABAQUS, so in CAE. So what I have done here is I have created a general contact. So if you are not familiar, again you can look at my videos on how to create general contact, but Just to show you, you just press create, you select name it, and then you say general contact. So in general contact, the advantage is you don't need to really select the surfaces and everything. It automatically selects it for you and when the contact is established. So if you press continue now, then you will see it will take you, sorry, it's already there, so it's not going to define me. So it will, this window will appear. I have selected the default values, and for interaction properties, as I told you, I have used interaction contact properties, and then in that case I define the normal contact as a hard contact, as I explained in the slides. And for tangential contact, I have used you can use frictionless for the few steps, but I would say just go with penalty, and you can apply 0.0 for frictionless case and for 0.5 for this case. So, and then it will automatically be here. So this is how I define the contact. If you want to look at the interaction properties, if you don't believe me, I just show you. This is the tangential behavior, which is penalty and 0.5, and normal behavior is hard contact, and nothing, everything is default, as I told you before. Next thing is to go to the loads, and this is the most critical step. In the first step, we are going to apply a gravity load. So you see, you go to step 1, you press create, and you select step 1 here, and then you select gravity load, right? And when you apply gravity load, so you will get this window. Once you press continue, you'll get this window, and in this case we are applying a acceleration due to gravity, because this is applied in terms of acceleration due to gravity in negative y direction. So that's what I have given here, and rest are all 0, and it will be applied to the whole geometries and everything which is in the model. Next thing is to define the boundary conditions. So we have 3 steps. So as I told you, this side of the seabed will always be fixed in all directions. So that's what I have done here. All the directions are fixed here. And similarly, this end of the pipe will also be fixed. So you see I have fixed the pipe as well. So this is basically for the seabed, and the one previously showed, it was this one, is for the pipe. And so both of these are fixed permanently and throughout. That's why this propagated throughout. Then we fix this surface seabed from this reference point only in step 1. So that's, you see, it's everything is fixed, but only in step 1, and I have deactivated in step 2 and step 3, because in the second step we need to move this thing down. So we need to apply the second boundary condition, which is this one, and here I'm applying a vertical displacement of -1 meters to create that imperfection for step 2 only. And you see it starts from step 2 and it goes up to step 3. And finally, also in the final step, when we apply temperatures, we need to fix this end of the pipe in axial direction as per the requirements, and that's what I have done here. U1 is 0 for this end of the pipe. So this is how it looks like for boundary conditions. So again, based on your own problem, you have to really carefully look at how you are going to define all the boundary conditions for different steps. Now for the temperatures, I have created a predefined field for temperature, and it will only be activated during step 3, which is a step where we will apply the temperatures. And if you look at that, so I have applied a temperature of this, and also I have given an amplitude function because I want the temperature not to apply it instantaneously, but increase from 0 to 120. So I go to tabular and I say that at time 0 the temperature is 0, and at time 1, because total time of the step is 1, the temperature goes to 120, and this means, or 1 in this case, because it's an amplitude function. So 1 times 120 will be 120, so it will increase linearly from 0 to 1. So that's what the amplitude 1 here is. Okay, and this is only active in step 3, so we don't have anything related to that in step 1. So this is all about the loadings and boundary conditions. Once you are happy with that, you go to the mesh, and you have to mesh the part individually. So for this, again, I have used an element size of 5, which is irrelevant in this case, but just to improve the contact conditions, because your pipe will basically be making contact with this too. So to avoid anything, I have used this size, but you can play around with that. So this may not be optimized. And the element type which is used in this case is discrete rigid, which is R3D4 elements, and in explicit, which are linear elements. Okay, for part 1, in this case I'm using a global size of 10, but again you can play around and you have to do mesh convergence studies to see which one suits the best and gives you the best results based on your experimental data. I have just, for this series case, I have done that, because even this, with this many elements, it takes couple less than 1 minute or 2 minutes to solve, so it's okay for this case. If you look at the element type, so you see I have used explicit linear pipe elements, and these are called pipe 31, which are two noded linear pipe in space. Space means it's a 3D, it works in 3D, although it's a 2D two node element. Yeah, so that's what the finite element mesh looks like. You see pipeline and everything is mesh. So these are rigid elements and these are deformable pipe elements, pipe 31. Then you just go to your analysis and you submit. So just to show you how long it's gonna take, I will just run it and I hope it works without any problems. So now it's submitted, and now after completion we can go to the results, and this is how it looks like. So you see you have, so this is the whole pipeline. You don't see much on this side, but if you go closer then you see what has happened here. You basically have this thing moved down and you have some buckling, as I showed you. How to create those animation videos which I showed you just now, you can basically create more viewports. So you say create viewport, maybe another one as I showed you, and then you can arrange them. You can arrange them in many different ways. I'm gonna quickly, I will do it vertically. So you see this is the how it looks like. This is isometric view. This is isometric view. This is we can make this one as the front view, so we can just zoom in. Yeah, we can remove all these decorations from viewports as well. So if you go to viewport annotation option, so you can remove all this stuff to make it more better visible. This one as well, and this one as well. Okay, so this will look like. And here if I want to plot, let's say the stress strain curve, so if I go here and I need to go to find the node which, so I will remove the, I think the surface. I can remove, I can only keep the pipe surface maybe, and then I just zoom into this edge which was fixed and I will plot the reaction forces here. So you go to tools, Square Data Manager, and then I will create, okay, there is a lot of data there, so I'll just remove those. I'll just say create ODB file, and then yeah, we need temperature, and we also, so first let's go with the temperature thing, and I just select one of the elements here and press done and save, because each element can have many nodes, so it's just plotting all of those and many integration points, sorry. So now I have to do for the same for the nodes. So element unique nodal, and in this case I need reaction force. So I can plot the reaction force, maybe I can plot the magnitude, because this will only be reaction force in one direction, which will be equal to magnitude in this case. Then I go here and I select the node. So if node is selected, then I press done and I press save here. Okay, so now I have the reaction force as a function of time. As you see here, from 0 to 2 seconds there is nothing happening because there is no temperature increase, but after that your temperature increases. So you see this is how it looks like. So as temperature causes this, after the imperfection is there. So now I'm going to combine these two and create the plot which I showed you in the animation. So I go operate on XY data, and then I say combined. Then on horizontal axis I need temperature, on vertical axis I need the reaction force or the total force. You can name whatever force versus temperature, and then you can plot that. So you see this was the plot I showed you. If this is too small, you just double click on it and you can change their fonts from axis. So let me make it bigger, hopefully. Yeah, and then this one as well. Okay, I need to take this out, and then I just do the same for this one. In this case also it's 24, so, and now it's visible. So you see the temperature goes from 0 to 120 and how the force increases. Again, to validate your own model, you have to use your own boundary conditions, loadings, and the material properties, etc., friction properties as well. But also you need to do a mesh sensitivity analysis, as I haven't done that, and you might have to change and play around with different types of mesh to see which one converges or gives you the right results. So another thing was animation, how I did that. So in this case I have isometric view. As you see, here is the front view, here is the side view. Again, you can arrange them in different ways. There are different options here, horizontally, vertically, whatever you like. Okay, and then okay, so for animation I go here and you see it starts to animate only this part. So what I can do now is basically I have to link all the video, all the viewports. So I'm going to link them. So now you see this lock sign, so they are all going to work together. And if I can now show the animation, so I have to go for animation for all of them. So this is already there, so they are all running most probably now. So this is the second step, and now you see as the temperature starts to increase or kicks in the third step, you see this buckling going or start to occur because of this imperfection. And then after post buckling, when you have reached to the critical load, you have complete collapse sort of thing. So I hope I was able to convey how to create this kind of job, and hope you have learned something from it. So if you have any questions, again, get back to me. If you have any other problem which you think you are struggling to solve, then just create a one page or one slide description of the problem and email us on 3minutesengineeringconcepts@gmail.com, and we will come back with this kind of solution as you are seeing currently. So see you then. Until next time, bye for now.